that I didn't have time for yesterday, and then we'll go on with lambda calculus. So here's a useful one. I'm not going to say too much about it, but just to let you know that it's here. Coq has lots of specialized built-in tactics or library tactics that people have contributed. One of them is a library called Omega that implements Bill Pugh's Omega decision procedure for Pressburger arithmetic. And so it's quite convenient if you find yourself with kind of simple arithmetic constraints and you're annoyed doing all of the low-level arithmetic manipulation, try Omega. Okay, here's a few more just to mention them quickly. Clear deletes a hypothesis from the context. That's useful if you've already used it and you're tired of looking at it. You just want to simplify things. Subst with a variable name just substitutes away that variable without clearing out the other equalities in the context. Subst with no variable name is useful after like an inversion that's generated a whole pile of equalities that you don't want to think about. Rename is useful if some automatic tactic has chosen a bad variable name for something. So it's a kind of post hoc as. Assumption, we saw once a couple of days ago, is a tactic that looks in the local hypotheses for something that can be applied to solve the goal. Contradiction is similar. It looks in the local hypotheses for something contradictory, something equivalent to false, and solves the goal if so. Constructor is a simple one that looks around in all currently available inductive definitions and sees if there's some constructor that can be applied at this point. Okay, so these are all pretty easy to use, and there are a whole bunch of others that you'll find kind of as you go along, reading other people's scripts and so on. But we're now getting on toward a fairly complete set. In a few minutes, I'll come back and talk about just a couple more substantially more powerful automation techniques. But first, let's quickly finish up the treatment of IMP. So remember, we had this little imperative language. We had arithmetic expressions, Boolean expressions, and then commands. We were in the middle of defining the semantics of arithmetic expressions. So we had given the semantics as a fixed point, and then we got drawn off onto this side topic of proving that the optimization was correct, and then noticed that it would be nice to have a little automation for that. So coming back to the mainstream, here is evaluation presented as an inductively defined relation as opposed to a fixed point. And there's not too much to say about it. It's just it's a scheme for let's take a little look at it. It's a scheme for the way kind of all inductive definitions of inductively defined relations are going to look. So first of all, one little notational trick is we've seen that we can define something and then afterwards define a notation for it. With these complicated inductive definitions, that's a little bit unfortunate because you have to give this big long definition in terms of the low-level notation, which you're never again going to use. But now every time you have to refer back to this big definition, you're seeing it in terms of the wrong notation. So what you can do to fix that is use this reserved notation trick. So you first declare the notation. You kind of reserve a place for it in the parser. You then give the definition using the new notation without yet having said what it means. And then at the bottom of the definition, you say where and specify what it means. So this is useful. Okay, so aside from that, I'm not sure what there is to say here. So this is, notice that here all of the parameters, both of the parameters to the inductive definition are non-uniform ones. Why? Because, well, they're non-uniform, because in each of the clauses, in each of the rules forming this inductive definition, the arithmetic expression to be evaluated and the number that it evaluates to are different. Okay, so not too much more to say about that. Then, as usual, so this will be the standard pattern all the way through, we define ourselves a little A-eval R cases so that we can easily do inductive proofs. So I think probably all of the, every year there are a couple of people from the Coq team kind of hanging around. So I always like to plant the seed, so just in case there's anybody in the room. This should be built in. It's silly to have to do this every time. And indeed, Alexandra Pilkiewicz made a beautiful plug-in for a beautiful extension for Coq that handles all of this completely automatically and is wonderful and beautiful. And the Coq team has so far chosen to ignore it, and they should not. Okay, so we can prove theorems about this. So here's the kind of long version of the theorem, and then if you want a little exercise, I'm sure you have plenty, but if you want an extra, it's a nice little exercise with tactics to crunch this down to something more like what you would write informally. Okay, but let's go on and finish the definition of IMP. So what's left? So we had kind of bare arithmetic expressions, and we didn't bother dealing with variables before. So let's now add variables to the arithmetic expressions. We do that by, okay, so the top definition is worth talking about for a minute. So essentially that top definition is making ID a synonym for, or not quite a synonym, but is making another type that is isomorphic to the type NAT. All right, so it's just wrapping an extra constructor around it. Why would we do that? Same reason we would do it in Haskell or ML, abstraction. So I'm going to use numbers as my identifiers, just to avoid the silliness of getting involved with the Coq string library and all of that. So I'm just going to use numbers as my identifiers, but I don't want to confuse these numbers with other numbers that are not identifiers, and I don't want them to show up as just NAT when I'm looking at some expression. I like them to show up as ID. So let's create a fresh type wrapping up a NAT as an ID. And then all the things that I used to do with NATs, like test them for equality, I need to define new versions of, so there's a little bit of overhead. But once that overhead is finished, I can just use them as their own thing. And by the way, I'm not going to say anything about this at all except tell you that it exists. A Haskell programmer looking at something like this would say, well, defining a new name, BEQID, is very silly here. We should just have BEQ, and it should be a type class, and ID and NAT and everything else should be instances of it. And you can do all that in Coq. The reason that the SF notes are not written that way is twofold. One, that all of this stuff was started before type classes were added to Coq. So it would require going back and changing. And then second, we haven't felt motivated to do the change because type classes are one more thing to explain. And some of the people that we teach using this material are complete newbies and have no idea even about functional programming. So that seems like a little bit too much extra overhead. For you guys, we should just start with it the type class way because it would make perfect sense. Okay, now we need to represent memories. There are different choices here, and they all work. But this is a perfect illustration of a general truth about not just Coq, but any kind of mechanization of mathematics, is that little details about low-level choices make an enormous difference in how easy or hard it is to get work done. So here, for example, we've chosen a representation, a functional representation, where the memory is a total function from identifiers to numbers. Other alternatives would be possible. So we could have an A-list representation, or lots of other ones that you could think of. And we have tried those, and they all work. You can get to your goal, but this one is quite a bit smoother and cleaner for low-level reasons that I don't actually even remember anymore. But the point is that if you try it a different way, if you try it a particular way and find that you're doing a lot of kind of low-level plumbing that's annoying you, try changing the definitions. Keep looking for the optimal definitions for doing the reasoning that you want, rather than just take the definitions that you had on paper, transcribe them into Coq, and try to power your way forward. That will work, but at the cost of very much unnecessary pain. Okay, and then we need some little lemmas that say, you know, if you store something in the state and then look up that variable, you get the value that you stored, and several other similar things. Okay, now we're ready for, now we can add the variables back into the syntax of terms of arithmetic expressions, and redo the evaluator, and that's it. That's it for the expression part. Now we can do the command part, and I'm going through this fairly quickly because I think at the level of the programming language part, none of it is very surprising. But so here are commands at the top, the usual COM cases. At the bottom of the screen is a little bit of notation. So here we did put a little bit of time into kind of figuring out what was the least horrible way to make Coq parse expressions that look sort of like while programs. You'll notice that the arithmetic and Boolean expressions that are embedded in them don't have like binary operators for plus and things like that. In previous versions, we did try to do that, and we eventually ripped it out. It got too ugly. So because, for example, like what identifier would you use for plus? Well, you can't use plus because that's the one for numbers. Okay, maybe plus plus? No, that's used too. Okay, plus plus plus? Well, yes, but now it's starting to look like diminishing returns.
One thing I found to be very useful is to use the scoping for notations.
That's right. So one thing you can do if you really care about having nice notations, important. So we didn't go that far. But one thing you can do is the notations in Coq are scoped. And you can define your own new scopes, and then you can tell the parser, now I'm going into this kind of scope, and it will interpret the notations in that way instead of whatever way you had said by default. Yeah, so thank you, that is useful. All right. Yes? Overriding notation is pretty hard in my experience. In general, I don't consider myself a super expert in the notation aspect of Coq, and also not in many other aspects of Coq. But I'm sure you could drive it harder than I have if you really, really cared. But I have found it pretty painful to work with when I've tried, so I tend to stay with pretty simple things. Okay, now we need evaluation. And the story here is pretty simple. You can start with trying to define evaluation as a fixed point. And you quickly realize, oh, this is one of the cases where fixed points don't work so well. Why? Because evaluation in this language is not a total function. So now you can play all sorts of games. If you really care about it being a fixed point, you can play various games. So you can, I think probably the best way to do it is to step index it. I use that term advisedly. So what I mean is you can add an extra argument to the evaluation function, which is a number, which is used as fuel basically for the evaluator. And so you start the evaluator and you give it a certain amount of gas. Right? I'm giving you 100,000 units of gas, and each time it makes a recursive call, it subtracts 1 from the gas. And so now it's obviously terminating, but of course it may run out of gas. And now you have to decide, well, what's it going to do when it runs out of gas? So it could like return a stupid answer, like return 5 always. That would not be very good. So then you say, okay, well, let's make it return an option, and it can return none if it runs out of gas. Now you start having to rewrite your evaluator with a lot of plumbing in it to deal with these options. You have to rewrite it in a monadic style, and so none of it is very satisfactory. So the nice way to do it is just to forget about all of that and write it as a relation, and there it is. Okay, so I think that is all. That is all I want to say about imperative programs. And at this point, I'm actually going to skip around a bit. I'm going to skip some chapters. Let me give you a little overview, those of you that haven't found this already. Here is the whole chapter dependency diagram for the whole book. So we've been through this part. And now we were looking at IMP. And at this point, if I were teaching a full semester course, especially to newbies, we would stay with IMP for a while. We would talk about program equivalences and then define Hoare logic for IMP. And there are even a couple of optional topics there. You can extend IMP with lists, and then you have some more interesting programs to do Hoare logic proofs about, and so on. I'm going to completely ignore all of that stuff, but now you know it's there, in case you want to have a look yourselves. The next topic after that, kind of in a straight line from IMP, is a chapter called Small Step, which I am going to completely skip today. But which you may want to go back and have a look at if the relationship between big step semantics and small step semantics is something that you wonder about. That is all carefully detailed in that chapter. So it takes, I think for arithmetic expressions, kind of does the whole thing in tremendous detail. Here's the big step version, here's the small step version, what's the theorem that relates them, and so on. Okay, and then we go on to talking about types. So there's a chapter called just types, which I'm going to mostly skip. There's a little bit of stuff in there about further automation, which we'll talk about in a minute. But then I'm going to skip the rest of it, which is just talking about a kind of simplest possible type system, a type system with 2 types, nat and bool, for simple expressions. Okay, so that would bore you guys, I think. So I'm going to skip over it and go instead to the simply typed lambda calculus. The simply typed lambda calculus, of course, itself is much simpler than the systems that we've been dealing with and proving things about for many days, and that you guys are mostly very used to anyway. But that's the chapter where I want to spend the rest of this lecture. Not because the system is so scintillating in itself, but because it's a good example. It's finally a sort of at-scale example of using Coq to formalize facts about a programming language. So we'll go through that chapter fairly carefully, and then use whatever time is left at the end to try some of the bigger proofs together. Okay, so that's my plan for today. Just to show you the rest of what's in the book, since we're looking at the dependency diagram, over here we have, so there's a chapter called More SDLC, that shows how to add like products and sums and records and all the kind of stuff that you would want in a programming language that isn't in the raw lambda calculus. So that shows how to add that stuff. And then a chapter on type checking, which develops a type checking algorithm for the simply typed lambda calculus and shows, excuse me, shows that it's correct. Then a chapter on references, showing how to have store typings and types for references a la ML. And then some chapters on kind of more advanced typing features, subtyping in particular, then records, and then records with subtyping. Then along the way, there are some optional chapters that we've skipped. So first of all, up here, there's a chapter which I think I'll talk about a little bit tomorrow, which is a parser for IMP. So nothing very much is proved in there, but it's interesting as an example of just programming using Coq's somewhat limited functional language, and fleshing out kind of going toward the concrete syntax part of the front end of an interpreter. And then this IMP C eval fun shows you some of these tricks, like the trick with a fixed point for evaluation for IMP using this extra fuel parameter. And then PE is a little chapter on partial evaluation. The yellow means that this is a contributed chapter. This is a chapter that was written by somebody other than the main group of authors. Just kind of added as a user contribution, as it were, to the book. There are some other contributed chapters that are useful. So norm is a chapter on normalization for the simply typed lambda calculus. I think Amal mentioned it yesterday. Following basically Tate's method, but adapted to the Coq setting, and this was contributed by Andrew Tolmach. And then these two chapters on the right were contributed by Arthur Chaguereau, and these are more extended tutorials on how to use the tactic features, tactic programming, and his kind of slightly fancier tactic library. And then a whole chapter on how to use the auto feature, which we'll talk about today. Okay, so this is just by way of telling you everything that's there, in case you want to have a look at it further. All right, so going back to where we were, let's look at this types chapter. Okay, so we're not really going to look at types. We're going to look at just the automation stuff. The auto tactic is Coq's most fundamental tactic for doing proof search. And what it does is basically exhaustively explores all possible proof trees involving only the following tactics: intros, apply, and reflexivity. even its use of apply is limited. So by default, it's willing to apply only things from the local context, not arbitrary theorems from the library and so on. So it's willing to deal with conditional statements by putting things into the context. It's willing to apply things from the context, and it's willing to use reflexivity, and that's all it does. It can be extended a little bit, I'll show you in a minute, but basically that's its core behavior, and it just exhaustively searches to some depth. I think the default is like 5. You can ask it to search a little bit deeper if you want, but obviously you don't want to ask it to search very, very deep, because that will take a long time. So auto doesn't always work. When it works, it's incredibly convenient, because you just say proof auto QED. That's all there is to say. Okay, now, you can extend it a little bit, as I said. So it has a notion of a hint database, which tells it, here are some things from the global context that you should also consider applying. And that hint database can be managed by you. So some of the things that we've already seen, some of the, for example, the constructors, conj, intro R, intro L, for OR, are pre-installed by the library where they're defined in the hint database. So auto will always look for those. When you define something, one more thing. You can locally extend the hint database when you use auto. You can say auto using and give the name of a couple of lemmas that need to be applied at this point somewhere during the proof search. You can, so that's kind of temporary extension of the hint database. You can also permanently extend the hint database by these kind of commands. So hint resolve, hint constructors, hint unfold. So hint resolve takes any theorem that you've proved and adds it to the hint database. Hint constructors is a kind of convenience. So hint constructors T, where T is some inductively defined type, adds all of the constructors. So it's as if you said hint resolve C1, hint resolve C2, and so on for each constructor. And then hint unfold is a little bit different. It doesn't add a theorem, but it allows auto to do a little bit of automatic unfolding, which it by default doesn't do as it's doing its proof search. So hint unfold may enable some other applications. It's also worth knowing that there isn't just one hint database. You can define your own. So as you're going along, if you find that there are certain proofs where you need a certain collection of facts very often, but you don't want them cluttering up and slowing down the hint database globally, you can put them in a local hint database. So auto is a power tool. It has to be used with care because it's easy to cut your foot off. But you will quickly learn to have a feeling for which sorts of things it's safe to put in the auto hint database and which it isn't. Right, so the sorts of things that are safe to put in are like constructors of inductively defined data types, because they don't apply very often. Whereas generic theorems like transitivity would be rather unsafe to put in, as that would lead to kind of wild proof search. Okay. One little kind of concrete syntax convenience is when you start a proof, you can say proof with and give a tactic. And then during that proof, you can say ... in place of that tactic. And many of the proofs later on will use that by saying proof with auto. Now let's see, where did E-auto get explained? I didn't explain E-auto. Let me explain E-auto. E-auto is a variant of auto that, instead of using apply, uses a tactic called E-apply. Okay, so now let me explain E-apply. E-apply, okay, remember when we discussed apply, we noticed that if there are uninstantiated metavariables after it does its unification thing, it will fail. You might ask yourself, well, why should it fail? Why can't it just remember that there was an uninstantiated unification variable and let me deal with it later? That's what E-apply does. So if you use E-apply in one of those situations where apply would have failed, you will get sub-goals where the statement of the goal involves some unification variables. You can recognize them because they begin with a question mark. And these are things that are going to need to be filled in at some point before the proof is finished. So if you get to the end and say QED and there are still uninstantiated metavariables, uninstantiated unification variables, then the QED will fail. So you have to discharge them eventually. But what's convenient is often the very next step you're going to do is going to nail down what that variable must have been. So it's often very convenient to leave it uninstantiated for a couple of steps. Okay, so E-apply does that, and then E-auto uses E-apply instead of apply. Why have both auto and E-auto? Because E-auto sounds much more powerful. Power is good sometimes, and speed is good sometimes, and that's why. E-auto is much slower than auto in general. So I would say my sense of what most Coq experts do is they liberally use auto all over the place, but they kind of think before they put an E-auto in their proof, because that will really slow down how long it takes for Coq to check that file. It's very useful sometimes. Okay. Another useful one is solve by inversion. This is just a convenience. So this is for situations where in the context there's something that if you invert it is going to give you 0 subgoals. So this just searches through the context, trying to invert everything it finds. And if it manages to find one that completely solves the goal, then it's happy. Otherwise, it leaves everything unchanged. Okay, so this is quite convenient sometimes. However, I need to add an even bigger caveat. This one can be very slow. So I've even heard it argued that this one should not be used at all, because it's just too, or that at least I shouldn't be teaching people to use it wantonly. So you should use it with care, because it can slow down your developments. But we do use it in our developments here because often it makes things just a lot shorter and clearer. You can just say, well, we're in a contradictory state. You figure out why. Here's another one that doesn't have a speed penalty and is often quite useful. It's a variant of try. So remember, try attempts to use a tactic, and if it fails, doesn't do anything. That is, succeeds and does nothing, rather than failing. Sometimes that's not what you want. Sometimes you want to try a tactic, but if it doesn't fully solve the goal, it's going to leave your goal state in a kind of mangled form that'll be confusing, or you don't actually want to continue in that direction. You just wanted to take one step, and if it didn't work, then step back. And that's what try-solve does. Okay, and then the last thing I'm not going to talk about in any detail, but just to let you know that it's here, is a tactic called normalize. This one isn't built in. It's one that we defined. But it's quite useful for animating inductively defined step relations. So in a little bit more detail, the downside of defining your operational semantics with an inductively defined relation rather than a fixed point is that now you can't experiment with it, right? Because every time you want to show that some term evaluates to something or other, you have to do a big, long, laborious proof by hand. Right? So you can perfectly well do it, but it's boring. And so you won't do much testing of your operational semantics if you have to do it that way. So this normalize tactic takes an inductive definition, takes a deterministic inductive definition, one that actually defines a partial function, and steps it. Okay. I think that's all I want to say about this file. Here's the definition of normalize, by the way. It's a few lines of tactic notation script. And a general comment about hacking in the tactic language is as you begin to be more expert Coq users, you will certainly feel yourself drawn to doing this kind of hacking. At the beginning, try not to go nuts with it for two reasons. One, because it's easy to kind of get lost in it and stop understanding what your proofs are about. And two, it is probably a tough contender with TeX for world's worst programming language designed by a computer scientist. So it's very useful. It can do lots of stuff, but it has many warts and weird subtleties and inconsistencies, and you'll spend a lot of time on it. So at some point in your Coq career, that will be useful, but kind of amortize that time over getting useful work done. Okay, any questions about automation and such?
So when something like auto, is there a way to record the steps to solve and give it back to you?
That is a good question, and I think the answer is no. But before confidently saying no, I would want to check with super hackers. It would be very useful to be able to say auto, take the proof tree that comes out. I suppose you could just print the proof tree and then cut and paste it. But one would think there would be a better way than that, and I don't know. Yeah, that would be really convenient. Or like, why can't it just automatically, cache it in a file someplace so that when you change your definitions and it actually has to do the proof search, then it would do it and it would take 10 seconds, but every other time it would just look up the term that it found before. These are small matters of engineering that nobody's gotten around to.
What would you say, print proof? Is that show proof?
Show proof or just print at the end. All right. Let's talk about the simply typed lambda calculus. So this is kind of a case study now. So the lambda calculus that I'm going to talk about is the simply typed lambda calculus over the Booleans. So I'll have Boolean constants and I'll have a conditional. And my types are just two, Boolean and arrow types. And my abstract syntax of terms is defined that way. And as usual, I need this T cases stuff. Should be term cases, shouldn't it? Anyway, for helping with inductions over terms. Okay, now we need for the semantics a notion of values. So values are true, false, and abstractions. We need a notion of substitution. And this is the usual definition. Actually, there's a story about substitution, which is a long story, so let's not do much of it. But the short version of the story is substitution is a gigantic pain in the neck. It's one of the biggest pains in the neck. In fact, I'm tempted to say the biggest pain in the neck that one encounters when formalizing arguments about programming languages. And the reason is that the simple, naive definition of substitution, this one, is wrong. So you probably all know why it's wrong, but let's just review. So it's wrong because it isn't capture avoiding. So if I take a term with a free variable x, and I substitute it into an expression that binds x with a lambda x, where the thing that I'm substituting for, say z, the variable that I'm substituting for appears free inside of that binding for x, the x binding will capture the free x in the term that I'm substituting in. And that's wrong. It's wrong because it breaks a fundamental principle of kind of what variable names are. Namely, variable names shouldn't matter. So you should be able to consistently rename or alpha convert a bound variable without changing the meaning of a term. So if I change that lambda x to a lambda something else, now the free variable in the thing I'm substituting in isn't captured, and the resulting term means something different. It changes from a constant function to an identity function or something like that, or the other way around. So with capture non-avoiding, capture incurring or capture encouraging substitution, the invariance of all operations, in particular substitution, under renaming of bound variables is broken. Okay, so this definition is wrong. So what can we do? There are many possibilities, and none of them is completely satisfactory. So one possibility, the one that I'm doing here, obviously, is live with it. What could that mean? The reason that we can live with it here is that it so happens that we're only interested in beta reduction, call by value beta reduction of closed programs. So if you think about it, if you take a closed program and at the top level you have a beta redex, then the argument must be a closed value. So, and we're substituting now a closed value inside of a lambda expression with just one variable. The result will be something, again, closed. And so, kind of inductively, we will always be substituting closed things when we do substitution. And when we substitute closed things, capture avoidance is not an issue. So, in the special case where we get lucky and all we want is substituting closed things, this wrong definition happens to work. Right? It's good enough. And that's good because we can avoid a whole lot of fuss. So that's what we've done here. Where would that break down? Well, it breaks down almost immediately if you go in any direction. So, for example, suppose we wanted to formalize system F. It's the kind of next thing past the lambda calculus. This trick would immediately break because in system F, you have a typing rule that involves substituting for free variables. Which one is it? It's the type application rule. It's the one that says if you have a function that wants a type and you give it a type argument, then the type of the result is the polymorphic type with the type argument substituted in. So that substitution is is performed during type checking in an arbitrary context. And the thing that you're substituting in may be a type with free variables. Okay, so this happy special case doesn't extend very far. What else can you do? Well, you can replace the you can replace the variable names by numbers, and there are different ways of doing that. They're all called some variant of de Bruijn indices, and that works, but it involves a lot of fiddly, low-level incrementing and decrementing of numbers as you go through lambdas. So you can make that work. There have been some very pretty developments, even large-scale developments using de Bruijn indices, and people have succeeded in making it work. There's a general agreement that although it works, it's pretty clunky. So people are looking for alternatives. The current preferred alternative, in my mind, is the locally nameless representation, which is kind of a hybrid. It uses de Bruijn indices for bound variables, and it uses alphabetic names for free variables. And there's a whole story about why that, although it's a little bit, the definitions are a little bit more complicated, it works out globally cleaner than the pure de Bruijn version. So there's the locally nameless. There's another one called locally named, which some people prefer. There are various forms of higher order abstract syntax. This is still actually a kind of active research area, and people are still making new proposals for how to best do this. Okay, so unless there are questions, I'm going to move on from that whole thing. Okay, so this is just something to be aware of. If you're formalizing larger things, you will need to deal with bound variables in some way. I currently recommend the locally nameless presentation, but recognizing that it's not perfect either. Okay, so that was substitution. Now, on top of substitution, we can define reduction. So in the STABS rule, which is the beta rule, we're using the substitution operator. Aside from that, this is just standard Coq notation for a standard call by value reduction relation. We're doing small step now reduction relation. Okay, and then on top of that, if you like, we can define a multi-step reduction relation. This multi definition we skipped over, but it's just the reflexive transitive closure of a relation. Okay, now we have typing. And once again, we need to make a representation decision about contexts. So, and the two obvious choices are we can represent contexts as, well, maybe three choices. We can represent them as total maps, as partial maps, or as association lists. They will all get you there, but I find the partial map gives you the most elegant proofs later on. So context is a partial map that is a function from identifiers to options. The empty map is the partial map that always returns none. Extend is the function that takes a partial map and adds something to it, or perhaps overwrites something that's there. And then a context is a partial map where the range type is types of the lambda calculus. And now the typing relation is the standard one that you guys could all write in your sleep. And here's how it looks in Coq. And now we come to the interesting part. So here, for example, is the progress theorem. And then we're going to have a substitution lemma and a preservation theorem, as always. But rather than showing you the proof, why don't we take a pause at this point and do the proof? So let's see. Okay, so here's progress. Give it a minute to catch up. There we are. All right, so let's prove progress. So let's remember what progress says. It says if T is a term and capital T is a type, and in the empty context, that's all we care about because we're doing top-level reduction of closed things. In the empty context, little t has type big T, then either little t is a value or there's some little t prime that little t steps to. So how shall we start this proof? I'll do the first step. Okay, that's my contribution. Now, how does this proof go usually, by the way? When we do it on paper? Sorry? So we do induction of the typing derivation, and then in each case we get to use the induction hypothesis, which tells us that for all of the subterms, either the subterm is a value or the subterm can take a step, and then in each possible case, we have to figure out, well, that means that the whole term either is a value or can take a step. Okay, so how shall we begin, really? Induction. Induction on, what's it called? H. Okay, we've got a lot of sub-goals. Could we tidy this up just at the outset? Yeah, so we had this has type cases. And then we wrap the induction H in parentheses, and then since we're at the outer level, we want case instead of S case or SS case. Okay, this is a little bit better. So now each of the subgoals is telling us this is the T var subgoal, etc. And now if I write case T var, that will double check me that we really are talking about the T var case. Okay, so now how do we prove this? Left, yeah, we certainly aren't going to succeed in showing that a variable steps. So we must have to show that it's a value. Okay, how do we do that? Well, I guess we'd better look back at our definition of value. Where was it? Here. Okay. Yeah, so there's something wrong here. So there's no way that the variable can have a closed type, or indeed any type. I mean, there are no variables in type. So there's no way that, to say it more carefully, there's no way in the empty context that a variable can have any type. So something is wrong. Because this is saying that x0, which is the variable we're talking about in the context gamma, has a type. That is, it's the result when we look it up in gamma is not none. So there must be something contradictory here, I guess. What is it? Yeah, so that's a good intuition. So where does that intuition come from? maybe comes from looking at the local context and observing that the thing we're trying to prove just doesn't look provable. Not inconsistent, but given just that gamma is an arbitrary context, and that looking up x0 in it gives us back a type that's perfectly possible if gamma is an arbitrary context, then we're stuck. Okay, so and the thing to notice is that some information got lost. Right? We started out with gamma being an empty context, and that fact is no longer present in our assumptions. It got lost along the way. So why did it get lost? So generalized dependent is the right answer, but to find it again. But why did it get lost? Let's look back here. So we did induction on H. H was not an arbitrary typing derivation. H was a typing derivation where one of the parameters was fixed. And the induction tactic was the culprit, was the one that lost that empty. So rule of thumb, never do induction on something that isn't completely, where the slots aren't uniformly filled in with variables. Okay, so we need to fill in that empty with a variable instead. How do we do that? Generalized dependent was a thought, but it's not quite the right thought. Remember. So remember empty as, let's just call it E. Okay. Oh, drat, that didn't quite work. Why can't it infer that implicit parameter? So empty, remember, is a function from, because the type of context is the type of maps, of partial maps, is polymorphic. A context is a particular kind of partial map. It's a partial map whose range is types. But empty is a polymorphic constructor. So implicitly, there's an underscore following that empty because implicit parameters was turned on when we defined it. And it's now failing to be able to figure out what type we intend in place of that underscore. So how do we fix that? At. So if we say at empty, that turns off the implicit parameter, and now we can explicitly supply the type parameter that we want, which is ty, the type of simply typed types. Okay, so now H is fully abstract. The E is remembered to be empty, and now we can try doing our induction again. Okay, does this look better? It does, because we still have that fact that gamma equals empty. Now, the fact that gamma equals empty is something we're going to want to use in many of the cases. And so, we needed to pull it out with this remember, but in some sense, the first thing we should now do is put it back in. So I'm going to suggest that in each of the cases, we do a subst E before we do anything else. Oops. Subst. What is it? Why didn't subst E work, actually? HEQE, sorry. No. Yes. Is that what I need to say? No, sorry. Yes. Okay. Well, anyway, that got us what we wanted here. Let's see if it gets us what we want in the cases to come. Okay, so now we're in the T-bar case. Let's go forward. And we do now have the information that we need to go forward, which is the fact that H is a contradictory assumption. So we're assuming that looking up something in the empty context, which is the constant none function, returns sum. So what we should use is inversion. Inversion H, or simply solve by inversion would work here too. Okay, and now we can see that we've gone on to the T-abs case. So what should we do in this case? So we need to know that either lambda blah blah is a value or it steps to something. I think it's a value, so we want to use left. Now, how do we show that it's a value? With VABS. And to avoid having to remember that, I'll bet we can just say auto. Yep. Because remember, every time we introduced an inductive type like value, we remembered to say hint constructors afterward, higher in the file. Okay. Yeah, probably would. Let's try. Yep. Okay, what about T-app? This is the interesting case, of course. So what do we need to do? Sorry? So we're going to prove the right branch, no matter what, because an application can always step. It isn't a value, so it better always be able to step if progress is going to be true. Okay, good. So now what? Now we need to provide a T prime. Where's it going to come from? From substitution, maybe, but not necessarily. Exactly. So we need to appeal to the inductive hypotheses, in general, both of them. Although there is one case, so we're going to need to extract the juice out of these inductive hypotheses. That's going to give us 4 cases, but actually 2 of them are going to be the same. Which 2? All right, so either T1 steps or it's a value, and either T2 steps or it's a value. So 4 cases, but 2 of them are going to require the same argument. Right. So if T1 steps, we don't care about T2. So really only 3 cases. So we should case analyze T1 first, because that'll allow us to collapse those other 2 cases. So how do we do that case analysis? So I heard destruct and inversion, and both of them are correct. So the exact difference between destruct and inversion is a little bit subtle, and I have started many discussions with Coq experts to try to get a really crisp explanation of when destruct is appropriate and when inversion is appropriate. And it seems that there is no crisp explanation of that. Here is the fuzzy explanation. Destruct is a much lower level thing. So it basically just corresponds to a pattern match on the inductively defined data. Inversion is a much higher level thing. The proof term that it generates is some big hideous stuff. And it's doing a lot more for you in terms of generating equalities and things like that. So a rough and ready guide is if you care about the proof terms, if you're going to be looking at them, try to use destruct, probably never use inversion. Usually we don't care about looking at the proof terms, so then basically you could almost always use inversion, except there are a few times when destruct is actually more convenient, and it happens that this is one of them. And here's why. If you say inversion, it's going to fail. If you say inversion on this hypothesis, it's going to fail. And the reason is that this hypothesis does not have an inductively defined type, right? It has a pi type because of this trivial assumption. It's possible to deal with that. So we can, for example, assert a little local lemma that empty equals empty, and then use apply in to get rid of this, and kind of peel off this part. That will work. Oh, you might think, why do I even need apply in? I could just, if I had that lemma, I could just apply IH has type 1 to that evidence, and then apply inversion to that. And that won't work because inversion demands that it be applied to a variable. So it's one of the few tactics that you can't just apply to an arbitrary expression. It needs a variable. Okay, so you have to fiddle around a little bit. It works fine. I did it this morning. It takes a couple of lines. But actually, in this case, destruct is more direct because destruct is smart about conditional facts. So if you say destruct to a conditional thing, it will destruct this, and this will become a subgoal that has to be proved. So in this case, destruct is a little bit simpler. So let's do destruct IH has type 1 and see what happens. Okay, so the first thing that happens is we get this trivial hypothesis that has to be discharged, and fortunately that one is, I think, is easy for auto. Okay, so now we have the interesting information that okay, so now we've generated two subgoals, one for the case where T1 is a value, and one for the case where T1 steps. So we're looking now at the T1 is a value subcase, so let's remember that. And now what? Now we need a case on T2. So we'll do it the same way. Oops. Okay. All right, so now we're in the sub case. Sorry, not what I meant at all. I'm sure that's going to confuse proof general terribly. So let me roll back to here and then roll forward again. By the way, I'm sure you've already discovered, if your IDE ever gets desynchronized from the underlying Coq interpreter, just go back a couple of pages and then go forward again, and it almost always fixes it. Occasionally, you have to kill off the underlying interpreter if things get really confused, but that almost never happens to me. Okay, so now we're in the case where they're both values. And now what do we do? So here's the point where, so we know that T1, we know that we're in the beta reduction case. So we need to construct the T prime. And what do we need to construct it out of? Yeah, so we know in our hearts that T1 is a lambda. We need to get Coq to understand that T1 is a lambda. How can we do that? From its type would be a good way. And so what would be a good tactic to try for that? Destruct might be a good one, or inversion. I'm actually not sure which will work better in this case. I think this morning I tried inversion, but let's try destruct now and see what happens. So destruct H. So that probably gives us several goals. Ooh, that gave us a bunch of new goals. But maybe a lot of them are trivial, so let's have a look. So this must be the variable case, yes. So this is the case, look at H1, where we have some variable x0 and it's a value. Oh, but that can't be, that's a nonsensical case. So perhaps we can, and a bunch of the other cases are going to be nonsensical too, right? So there's going to be a case where T1 was true, a case where it was false, a case where it was if. All but one of the cases should be nonsensical. And so we should be able to deal with them all at once if we can figure out what's the right tactic to do it. So what is the right tactic? Okay, let's try it just once and see what happens. Did that deal with that case? Yes. Okay, so that seemed to work, so let's be more ambitious and put it after a semicolon. So at this point we have 6 subgoals, and at this point we have 8. Okay, so it seemed to deal with maybe all but one of the extra cases. Let's keep needing to make this window bigger. Okay. What do we need to do at this point? Where are we? Well, we do seem to be in the T-abs case. Here's the thing that's a value. And so we should be close to our goal. There are some kind of silly equalities in the context, so I'm going to suggest that we just substitute those away before we do anything else. And now look at it and try to think. So what do we want to do? So we have now the lambda that we wanted. So it's time to construct T prime, I guess. And T prime is going to be the witness for the existential. So now it's time to basically apply the existential introduction rule. Anybody remember which tactic that corresponds to? Exists. And exists has to be supplied with a value for T prime. And what's that value? So it's the body of the lambda, which is little t1, 2, I think. T0 is the type. So it's t1, 2, and then we substitute, and that was the notation we made up for substitution. It was x0 colon equals, and then what gets substituted in? T2. Okay. So it accepted that as the witness that we now have to justify. And here's the thing that we have to do to justify it. And what do we need for that? Auto, probably, because this is just a constructor from the inductively defined step relation. So I'll bet auto will get it. Yep. Okay. So there's a little bit more work to do to finish this proof. We have to deal with the remaining cases where it's where T2 isn't evaluate steps or where T1 isn't evaluate steps. And then we need to deal with some more cases about true and if and so on. But we've seen the pattern, and it's all either similar to or simpler than what we've just done. So we've kind of finished this proof morally. Here's your homework. Take the simply typed lambda calculus and add products. Okay, so take this file, STLC, and figure out all the things that you need to change to add product types and projections and pairing to the types, the abstract syntax, the typing relation, the evaluation relation, and all of the meta theory. So it's a really nice exercise, and even if you're a little bit behind on exercises, I would urge you to maybe even just jump ahead and start into this one, possibly picking a partner if that feels like too much work to do by yourselves. There's a lot of fun to do in pairs. And just what's fun about it is it steps you through every place. It forces you to think for a few seconds or a minute or two or sometimes a little bit longer, but it's a relatively straightforward exercise that takes you on a little walk through the complete formalization of the basic meta theory of the lambda calculus. So I really recommend that you try this one. Okay, enjoy your coffee.